Eccoci di nuovo qui per la seconda
So
parte.
here we are again for the second part of our lesson. We had left with a question, which was about this topic of the efficiency and costs. But I would leave out for a moment, since until now we have been a little bit destructive. Now I would begin to build. I will start talking about the Polytechnic, and then we will resume the question later. So what I would like to say in the meantime, to tell you quickly what we can do at the Polytechnic on the issue of health, also because we've invested a lot in recent years. And I would say in the last 20 years in terms of teachers and students of biomedical engineering that come to us from the other parts of Italy and the world. But over the last 3-4 years, we have also invested a lot in terms of equipment and space and research. So we think we have our own say, despite we are a technical university. So essentially you are at your first years of university, and the Polytechnic is still unknown to you. So I'm going to tell you a few stories quickly, and I think they can be useful. So meanwhile, let's say Polytechnic is divided into 11 departments. So we have 11 departments that are essentially the seat of all the educational and research activities. So I would say the structures that we could say from an organizational point of view, they're vertical. So, and the depositories of discipline. So within the departments, if you want, we have knowledge. Seen from the outside, the Polytechnic might seem as a monolith, and we have, it is not so. In reality, we have very different skills. It is interesting to talk about interdisciplinarity, as Professor Pievani reminded us, even within the Polytechnic, although it's limited to exact sciences. So we have the 11 departments here, vertical structures. We have industrial engineering, energetics, mechanical, aerospace, and one of applied sciences and technologies. And we have information department, information technology, electronics, computer science. And then we have 4 departments, 2 of architecture and 2 of civil engineering and environmental architecture and industrial design. And then we have 2 departments that put together are a bit different. One is mathematics, that obviously helped us setting the basis, and the other one is basic sciences, that physics and chemistry, and are with the Department of Applied Sciences. And then there's the Department of Production of Management Engineering. So these are the structures at the Polytechnic. And apparently a monolith, but in reality we're very different. Polytechnic is big. Often people did not talk to each other. Rather than not talking to each other, they didn't work together. But in 2017, the Polytechnic, also following examples of prestigious foreign universities, decided to create departmental centers. Instead of being vertical, they are horizontal departments. So they put together different disciplines towards the challenges that society proposes. So the idea is dynamically, among other things, because maybe the center that today is here, tomorrow could be different. So new challenges, new ones are always born, but it brings together the skills and different. Therefore, here we have a few more, because now we have almost 14. And here we talk about sustainable mobility, we talk about water, photonics, and innovative photonics. We talk about energy, And there are different types. We talk about collaborative robotics, we talk about electronics, power, among the different ones. You see, there's one that is called Polito Biomed Lab, which is I'm honored to coordinate, which gathers all the colleagues of the Polytechnic who are interested in health. Basically, let's say each one of these centers gathers more departments, and the one I will tell you briefly about, because it wants to be the answer to everything we said before. Before we destroyed a bit, now we want to build. It has 7 departments involved, and therefore we have mathematics and environment territories, and altogether 7 departments. Clearly the biggest ones, they live, and the colleagues that teach to a degree a course of biomedical engineering. What is interesting is that the Piedmont region 2 years later, probably they understood, or we understood, where we were going to, decided to create an open access search infrastructures. So basically is I help you to create this infrastructure, but then you make it available to companies, to industries. So open, it means non-discriminatory, but also that could work with reasonable activity and so on. And so it was dedicated towards small, medium businesses, and so and small and medium sizes enterprises were also involved. So also business and certification and technology transfer. And most of our centers that we had founded, they received the so-called booster. So the region added additional resources to the Polytechnic. We don't have large numbers, but these are they invested 3 million euros of fresh resources on, for example, our center on biomedical engineering, and the region added 2. So now we have a search infrastructure called pastis, which make you think of the aperitif, makes you think of our Piedmontese dialect. It could also mean something complicated or simply a mess. Unfortunately, if you go see the Risorgimento defense was called this way, because the idea was to have something complex but effective. So complex in terms of keeping together different several ideas, but pastis also means a technology part with different innovative technologies. So what's the idea? The idea is to respond, obviously, to challenges that we get from society, especially as regards health and well-being. And the idea was that of bringing together colleagues who come from all departments. So clearly biomedical engineers who have joined, which by their nature operate in this sector, but all those who instead for their specific skills and interests have participated at this time. The colleagues involved exceed 70 units. So one of the centers that has the participation of more colleagues and financing this initiative, the Pastis initiative. The region has joined also from the skill point of view, not from the equipment point of view. Colleagues of the University of Turin, especially those on the medical area, because we have, for example, for the past year, a doctorate called Bioengineering and Medical or Surgical Sciences. They're done jointly by medical colleagues who sit at the same table as engineers. So as I said, the purpose is, as I said before, like Professor Piovani said is not that of basic research. Remember, Professor Piovani spent important work regarding the importance of basic research, respect to which I will go back later. Here is the opposite. It's the technology transfer. The topic is if you want the most applied research we have a number that is called TRL, which is the proximity of an idea from the market to the market. So the first we have TRL 1, 2, 3, that's about basic research, and then we have proof of concept, and we shift more to industrial research for small, medium enterprises. So there are many colleagues who are involved. I'm just giving you this short description just to give you an idea of what we can do at the Polytechnic. So we have 3 pillars. One is called integrative biomechanics, and then we have information and communication technologies, that is closer to computer electronic information sciences, and one of these, both if you want, and then we have a part that instead works on the small, on cells, from cells down. We called it new materials and nanotechnologies for bio applications. Here we see some images of the 3 fields that I will briefly summarize. Let's start from here. You see, I will show you quickly 2 things: the facilities, so what we have purchased and what equipment we have available, and you will probably work on this in the future, and in this infrastructure, what are we doing with them? And here we start from the parts of biomechanics. And for example, we can say that we have test machines that allow us to test materials, devices, doctors, prostheses with different scales. So let's start with 2, the so-called the nano indentation equipment. There are machines that have a resolution of nanonewtons and nanometers, and therefore the test machine is a machine that, in a nutshell, measures forces and deformations of the objects that are subjected to the forces. So the first thing that comes to my mind is characterizing, for example, a material to find elastic shape, to say the simplest thing here. So let's start from objects that are able to do very detailed tests with very small forces, and then continue to mesoscale. So we have dynamic machines that are able to work both the axial and the biaxial plane, for example, to characterize tissues that naturally work in a state of biaxial tension. For example, I'm thinking, the skin, for example, that of heart valve, and then they can grow. And then we go instead to the field of prostheses, that we go from 3,000 in short to get up to 15,000 newtons. And we also able to have here, beyond the biaxial machine on the plane, we also have the machine that is able to simultaneously apply force and torque. And then we have machines that are capable of making the so-called digital decorrelation, which it basically means the open field to be able to map deformation. So you're in your first years, perhaps not everyone will be interested in topics of mechanics, solids, and yet fundamentally it is important to understand for the integrity of a structure, and yet point out there are stresses to deformation. And we also have to see, we are able to see instead dynamics of high frequency vibrations. We have infrared cameras to see phenomena that also affect the cells going to peak. And then we also have devices instead for the faster less meters, that is for the tracking of particles. And then we have fluid And then we have a part of fan mechanics, of ventilation mechanics. We have a simulator, for patient simulator here. It was not planned, but COVID helped us to develop this part as well, because during the COVID, together with a small medium company called PR, we patented and we are developed. And here we've been financed by the region a pulmonary ventilator. So we also need the simulation. We have a puppet patient that can simulate physiological breath. And then we also have the cardiovascular part. So we are able to generate ventricular flows with natural pulse system, physiological or not. We also have the simulacra of various aortic vessels, more descending or ascending. Here, not we imitate reality, because small or medium-sized enterprises have to validate their devices. For example, for a anti-embolic filter, and we're able to do it. Instead, we're working on the completion of this equipment that will take place. And then we're working with this collaborative robotic arm, and we have the idea of using in substance for usability test that is very important. And this is essentially to verify that this particular device can be optimally used, not only by the operator but also by the patient. So we actually think the idea is that of simulating surgical operations. So we basically copy the movements that the surgeon is making with a robot, but the surgeon is not able to tell us the forces he's applying, the speed of the movement, but the robot can. And so, in addition to the fact that I was telling you before, that instead of being through basic research, here we have that connected with the technology transfer, but also as regards medical devices and drugs, is the concept of the topic of certification. That is how, because everything that is sold in Europe needs the CE mark. It depends on what we're talking about. It can be very difficult to obtain. And here you understand it is obviously so. So I would say it's being developed in the Polytechnic, but we're dealing with certification. So we help companies to draw up the famous technical file. That's the basis to obtain a certification, because it's some papers that need to be filled up. And also there are some experimental testing that needs to be carried out, especially as regards clinical trials. And unfortunately, because things, remember efficiency, things should be done when they needed. So we are also active here, also as regards testing phase, trial phase. And also it's very important for abdominal and gynecological surgery, also for for treatment of hernias and inguinal abdominals. So we work on this. I will move on to the next concept, also the electromedical devices. There's also an electrical part that further complicates certification. We're working on that, for example, for the ventilator, because it's an electromedical device. So here you have some image. You see what we do for surgery, for medical device testing. All these are all testing that concern certification, not the development, probably sometimes the product is even being sold, but so here the only development is the one to the left, that's a laryngoscope that is not in the market yet, and other devices for orthopedics. So most of these activities that unfortunately again are carried out experimentally. Why I say unfortunately? Because experimentation is expensive. They can be done in silico. In silico means in numeric simulation. So in vivo, in vitro, in silico, ex vivo. So ex vivo means taking samples from the patient, in vivo on the patient. So we can do a lot with a computer as we do in all other fields. Here it's less common, but we will go back to this. Why is it useful? Because clearly costs are much lower and we can be much more efficient, and often companies ask us to do the classic experimental test. We associate the test to the numbers to prove. I could already say it before. We provide the evidence, and we also make scientific publishing to this. And also we recommend how to improve them in order to make them more efficient. So the same as you've seen here also concerns stents. Here we are proving to prove the biomechanics. Here we are showing the stent for a mechanic replacement aorta valve. So moving on to the other areas, now I'm going to show you what we have, the ICT area. So the information technology and communication. Here as well, the purpose is that of if you want, maybe it's in a smaller scale, but associated to the previous one, we want to develop devices, tools, algorithms, models, strategies to understand the system that works in physiological conditions, and understand even when they are in pathological conditions to be able to make correct diagnosis. So what have we bought? What do we have available? We have a big piece of equipment that concerns the surface electromyography that allows you to measure muscle activation and then understand the various muscles and what timing they're made to intervene, what strength they are developing, and clearly putting in contact in relation to other things. We have open ultrasonic machines. What does it mean? When you go, you do an ultrasound in the hospital, the doctor takes the equipment and the result comes out. But the doctor cannot act on the parameters of the beam of the ultrasound. So we have an open ultrasound and we can change the power being used and so on. We also have all the system for the acquisition in an open way of electrophysiological signals. So we do not have the EEC by itself or the EEG by itself. So we have a very important topic in research, also as regards the PNR. So the topic of increasing the effective supply of health through telemedicine. And we have hardware and software, and we have a group of colleagues that deals with a very important topic, that is that of certification of medical software that in the past was simpler, today is more complicated. So here I'll move on very quickly, so I can show you as far the applications of surface electromyography are concerned. We have both point and matrix sensors, so we have able to put them also in relations with the various, you see the matrix, where we can map the activated muscle as well. We also have machines that clearly allow to tire, like sports machines. The upper can apply tire upper and lower limb, but then it's very important from the point of the for view of the equipment, of the financial effort we have made. We have a large room, 70 square meters, where we analyze steps. It's made with optical system. We have 14 fixed cameras. We also have the possibility to do that at the person's home. We reconstruct the movements and evaluate the clinical diagnosis as regards, for example, rehabilitation from surgery, as regards to sports, or the recording of a surgery maneuver for then evaluated and use it. Here clearly, in addition to the analysis of the step that is made with optical systems and balls that are attached to the walking patient, there is the possibility of joining also the myography, surface myography that we said before. We have muscle activation. We have the subject that the posture. We deal with posture, but there are a lot of motions of movements that we do without thinking. But from the engineering point, control of the motion we do, it's extraordinary. But some bigger controls are put in relation with pathologies, with diseases. So, as I said before, as regards the open ultrasound and the acoustic photo, we played with machines. We do that, but you also want to play with algorithms. So we want to play with the analysis of the measurement. So we want to find, for example, the contours of a tumor mass rather than the thickness of a wall of a heart vessel, rather than the obstruction and so on. So we use sophisticated image analysis systems, which instead are made with a computer. We also have dedicated data center and infrastructure. And then, as regards acquisitions, here in this part, we have a dedicated microscope, which we would also like to make it work with a robot, as regards because pathological analysis is made manually, but we also would like to analyze the position of the image. For example, a sample taking for a histological examination, but also, let's say, in the report following the analysis. I told you about telemedicine. We are developing sensors, smart textures in this field. And then last but not least, like we have colleagues who are involved in biomedical software. Until last year, biomedical software was self-certified. So the manufacturer was drafting a technical document and then would start to sell it. Today, we have more safety implications. So we have 1/3 of what is called notified body capable of giving its approval as regards the development process of implementation of the software. So moving on to the last pillar, which is that of the small. So before, if you want, they could be categorized from the cell up. Now we go to the cell down. We have different facilities here as well and different activities. Here there's some indication, some information on the activities that concern 3D printing, and then scaffold materials that are biocompatible materials, 3D printing for we would like to print not only scaffolds but also the cells. We have colleagues who have obtained a large European amount on this. We would also like to create the non-chip organs, a so-called organ chip that is take a part of that organ, make it grow in the lab, and then check only that organ microorganism created. So we are able to create the homes, the houses that are called scaffolds. And therefore we have the 3D printers that, unlike regular 3D printers, we have in the Polytechnic, we have an departmental center. We have one financed by the region which deals with 3D printing in a broad sense. And these are smaller, and they say much smaller size, but much more accurate. We also have machines that are able to characterize them, that will go under those nanometrics that we spoke about before. We have micro scales, quartz scales that are used to verify when the cell or protein has bonded with a cell, that are very accurate. We have a rheometer, that is a machine also that used for evaluating gels. We have devices for verifying the making of surface analysis. And also, two more words about this, which I would say we have a technical university. In Italy, there's not many technical university. We have 3 polytechnics, and then we have architecture in Venice, I would say, and then we have some examples abroad, but it's very rare the fact that a technical university has a cell culture, because to work with cells, we always had to turn to outside fellows, biologists, and here we're able to do cell cultures internally. And we also have machines to analyze proteins, and that it's working so well that in the future we will double this lab that works full time. We are also very well equipped as far as microscopes are concerned. So this is more, as I said before, the histological analysis is being made on different levels. So we have a cofocal microscopes. They're called with focal lens or spinning disc, so they can analyze thicknesses more important. We also have a 3D, and it's fundamental for the analysis of biological tissue cells and things of this type. So we have this is also essential for this. As regards BioNano, we have started certification activities in the nucleus, as I said, after technological innovation. Here we have ISO 10993, that is the biocompatibility. So, that being said, I will try to connect the two parts. I'm going back now to the slides that we looked at during the first period. So, the price is high and technology does not enter. So often when technology in industrial sectors, technology enters very strongly. In this field, technology enters with extreme difficulty because the market is closed in a way. There's not so much competition, so anything that is added, that we want to add, it means to give something more to the company. So often, and it's a paradox, technology enters with much difficulty. I make you an example, but I could make 10,000, for example, in the region, Piedmont region, our health system provides 3 different systems in hospitals with consultants whose only job is that of having these 3 systems talk to each other. But what really makes me sad is that when I see we have technology at low cost, but they don't use it. So we don't need research to do this. We just want to do it. The question is, why don't we want to do it? We have more complicated cases, clearly, because we want to develop a mitral percutaneous valve. At the moment, we are not able to without operating the patient. So we need to invest, but there are technologies that are already low-cost technologies, and they're not being used. So we want to understand why. So the positive message I want to deliver is that, can we do something? Can you do something about this? What should we do? We have tools to reverse this trend, but to derive the system here and to allow us in the first place to have more and be more efficient. And if we find more resources, that's fine. But I will to do more with what we have, because we have shown that we have many resources that are wasted. So let's try to answer this question. Let's look at this slide again and connect the 2 parts. So one could say it saves lives. He said no. So we'd say the other thing could say, because if you want to make a fountain pen, you make it and sell it. Here it's a regulation issue, and then we have certification is a very high cost. I've shown you before that often, unfortunately, if the market is closed, if there's no competition, prices do not depend on that. I've proven there are cases where drugs have increases of 1,000%, although the certification. So it is undoubted that the certification topic is very important, and it will become even more important because since June last year, we were late, 1 year late because of COVID. The new medical device regulation came into force, and it's so important that here at the Poli, we have taken a specific course for because we need to know if we certificate medical devices, we need to know where they are. So the topic is that a few years ago we were supplying good engineers, but they didn't even know what certification was about. So the new medical devices regulation, unfortunately, it's much more restrictive than the first one. So we expect a very important cost increase. You could tell me, okay, I understand, but it's important. Yes, it's important. And price increase that we have to apply also to what we already sell. But we need to consider this as well. We need to bear this cost as well. So we are taking care of it. We want to provide a service, but we can reduce them. Here I don't have the time to deal with this, but I tell you the basic problem is that probably this regulation was written by people who deal with drugs, and it was written, let me exaggerate, as if engineering didn't exist. So the topic is that anything you have to do, first you do the clinical trial, and then you put it on the market, which is typical we do with a drug. We cannot calculate a drug if we don't do a trial. Maybe in the future we can do. We have colleagues who are involved in design. We are forced we have to do the trial. But not everything is like that. So you've seen some figures before. We had plates, and we're trying for the synthesis of fractures for trochanteric fractures and so on. So do you want to tell me that we as engineers were not able to, when we know the material, the fatigue limit, the breaking loads, and the loads that are usually applied in that area, to design that device, and then we are forced to make fatigue forces that last 1, 2, 3 months. So you see, this is something we need as academics, we need to work on, because every time we need to change experimental or numeric part, we must do it. We would save a lot of resources, because if we save on these resources, we don't save to keep the save, but to use it somewhere else. So let's say to build, I'm a mechanical engineer. So if you want to build a house, you build a 10, then you take them down, you look when they break down, and you calculate how much it can resist an earthquake, for example, and then you build the real one. And then often the regulation loses sight of the practical use, because they focus on breakages. For example, orthopedic devices, logical, deal with a break, the design that fails from the point of view. But as mechanics, we know well that when something works, is not only the brake load, but also elasticity. And often these poor colleagues, these are very important expenses. They have to make a new medical device of this type, in addition to trying it in the lab. Let's say, I don't know about loads, but my other colleague sells this. See, this is what is called predicate analysis. So, like say, this one breaks at 10, mine does 12, and the authority that receives the information will say, okay, you can sell it. Also, this is a wrong way of thinking. Go back to the house example. If you want to build a house, so you look at your neighbor's house. If you make this size of pillar, you make a bigger size of pillar. But then, and then if you continue like that in the of the room, you have a big pillar. So, which means there's a lot of you can do. Instead of experimenting everything, you should avoid experimentation on patients, because after having finished in the lab, then we should experiment on patients, and then again another incredible huge field of in terms of consent, informed consent, privacy, and all this means costs. And clearly we cannot certify ourselves. We need to make all the tests, and then we go to an authority that is the notified body, for example, for this simple plate we were talking about, that tells us that it's okay. Also to make tests, we cannot decide. We need an ethics committee that first we tell them how we want to make it, how it sells, and we describe all the structure. And you see that these are important topics that clearly increase the cost of medical devices. Okay, I want to say one more thing, which turns out that companies essentially should fight against, they should try to gain freedom. But surprisingly, I discovered that large companies do not fight for it that often. They suggest the complications of the activities. Why? Because they see above, especially the big company, in this type of they see a sort of protection of their market. So the more the complicated is the certification, the less the small medium enterprise will not be able to sustain it, to make it. So this is a form of value transfer, but we have to keep in mind that this thing, we always should not lose the patient's perspective. It's the patient's safety, it's not the financial statements. So this is very important. We should not take it to the extreme, because it's another reason why technology cannot be included. For example, today, no one in Europe, no one would think. I told you showed you the European regulation, but then we have the FDA is probably more permissive. No one would think about developing a prosthesis in the operating room because that is not certified. There are no spaces, if we read this regulation, that pushes to continue. So we should never do always everything that is possible to allow new technologies who have no history to enter the market. So even here, unfortunately, the big company often sees this as protection of the market instead of the problem that becomes an advantage. So here now I present you a couple of numbers as regards Italy. You see the market is in biomedical industry is very important. So we don't have health employees, we only have devices, pharma, and so on. You see, we have 4,500 companies, 112,000 employed staff. We have a turnover of 16.2 billion, 10 of which come to Italy and 5 go abroad. And what is interesting is that of what is delivered in Italy, 78% is paid for by public health. So then we go back to what we were talking about. So who chooses? I choose for you, and you use it, and the third party is paying. So this is the problem. It's paid for by the public health service, and it's paid and it's chosen by the doctor, the physician. So the problem for us engineers and architects who deal with research in university, often we're cut off because traditionally, since this is the system, the doctor chooses and healthcare pays, where did the industry go? They go to the doctor, and it's correct they do it, because if they go to the doctor they would tell them we need this, this, and that. But the problem here is that often we're not sitting at the table, and instead we should be able to be sitting there, because we could be able to explain to the doctor that the carbon fiber device that he thinks it's like the Ferrari body, it's the same. So we should tell them that there's a hardware that costs $4 instead of that. So my message is a proposition. So we should be sitting there with the Indian engineers. We should be sitting there too. A few days ago, Roberto Burioni, you know who is? He said, engineers talk about viruses, a word where virologists design reinforced concrete bridges. It's not promising. I disagree with him because I believe that interdisciplinarity is very important. It could give a big contribution. We as Polytechnique, with the structures that we have put up, but also the point of some mechanisms, especially I would say that the task that I see most important is to talk to companies. If the big company doesn't want to talk to us, but I think it started to talk to each other too. It's to help small companies because a startup, the SME, do not have the strength to enter the market. We need to help them. If they come to us, we should help us not only to bring the product that they have already patented to be industrialized, but we must help them to make all the safety assessments so that it can be certified. And this way, clearly, all this increases the competition and, definitely cost reduction. So this is the positive sense. In a positive sense, is what we should do in the end is come together and we need to get into the game and have our saying. So like Professor Piovani was said, if you want, he somehow manifested, expressed not primacy, but the importance of base research, but also the importance of base research funded by public. So kind of primacy of public and basic research. I personally believe only partially in this. Yes, absolutely. We need the public funding that controls something. We do need basic research. Serendipity has explained to you that from basic research they can come out ideas, but also applied research is important in parallel, because even there things come out that we didn't know about. So I believe that the future and the challenge for the future is the combination between public and private. So undermining the concept that the private is only interested in making profit and public deals with things that matter. But if we sit at the same table, not only engineers and doctors, but let's say big public decision makers, also in a positive sense, not with hidden prices, but also big industrial companies, so that together they can solve and they can they progress and face the challenge that is in front of us. Why do I say this? It's very important, but getting to the end, I'll make you an example here. So to understand what's happening, what happens if we don't do this? Here you see there's no company, there's no nothing. This object, this is a piece of an esapode. An esapode is a sort of external fixing device that is used for difficult fractures. You see there are threads, wires that go through the bone, and we held them together with rings and we regulate. You all know with a stiff body has 6 degrees of freedom. So if we intervene with 6 wires, we can change the position. This is interesting. It was interested in Nizarova, who was a sheep farmer from Siberia, who had developed this technique that allowed him to treat, to heal his sheep who fracture their limbs with the rays of a bicycle. Now this system clearly there's some risk of infection, so this system is widely used and it's used all over the world. It has a lot of advantages, which I'm not describing now, especially compared to casting or to surgery. But why am I showing you this? Because that object you see there, from the mechanical point, seems like a rope that we use to hang our clothes on when we want to dry them. But you see, this object has a price of 800 euros. So mounting this, setting this on a patient, it's 800 per foot, and then we have the rings, and altogether the price for the device is 5,800 euros. And what is the result? And I'm not talking about the fact that the company says it can be used once because the wires wear out. So there's a whole market of disposable devices. So what is the meaning of this? What is the consequence? The manager of the hospital goes to the surgeon and says, I can afford a specific number per year of this, because after a while, if you really don't have to use it, use a plate, which costs much less. So especially, there's always a connection between cost and use, and this affects the patient. I met a surgeon in Milan who is Russian, who is a pupil of Lizarov, who has been of threaded bars of 10, and he's the best. And he's the best one in Italy who uses threaded bars with dices. So I would like to end my lesson with the last message. I think that for the reasons that I tried to quickly tell you, that it's a beautiful area where to work, because there's a lot to do, and I am convinced that technological innovation, differently from what is often explained, or maybe it's not told, is thought by health directors, is not the part of the problem. It's part of the solution. Technology is part of the solution, and it's what we can introduce, we can add with cost that can be compared to other industry, this technology within the system, because it will allow us not only to divert resources from other parts, but obviously to respond to the biggest challenge, that's the health of patients and of us in the end. So with this message, I will leave you at the Polytechnique. We are trying to work with small and medium-sized enterprises to work in this sense, and I hope that many of you will passionate about these issues to make your contribution in the future. Again, thank you, and have a good day.